Let's talk about ice. Why is ice so extremely slippery? That's actually not a trivial question, and physicists have been arguing about it for more than 100 years. You probably already know that molecules behave differently in different states. Like in liquid, molecules form weak bonds, but they still have enough energy to slip and slide past each other to fit the shape of their container. In solids, molecules are packed close together, often in a regular pattern, which helps solids keep a distinct shape. Because these molecules can often nestle closer together than they can in liquids, the solid form of a material is usually denser than the liquid form. But ice acts a little differently. Ice is the solid form of liquid. Oh my gosh, that's why ice is slippery. But ice acts a little differently. Ice is the solid form of liquid water. But depending on the temperature and pressure conditions, ice can freeze in a lot of different ways. In fact, there are more than a dozen variations of ice crystals, and scientists are still finding more. The most common ice is hexagonal ice. It's called ice 1H. 1 because it was the first kind discovered, and H because it's the hexagonal form. In this form, the water molecules form layers of honeycombs that stack on top of each other to form the whole crystal. These crystals take up more space than the same number of liquid water molecules. That means ice is less dense than water, so it floats. Another important type is ice 1C. Here the C stands for cubic, because in this form, the water molecules create a cubic-centered crystal structure. This kind of ice forms at colder temperatures than ice 1H, and can sometimes be found in Earth's atmosphere. As it turns out, these crystal structures are key to understanding why ice is so slippery. But scientists in the 1800s didn't know anything about them when they started studying the problem. So what did they think was going on? Some of the first people to try to solve the mystery were big names like Lord Kelvin, famous for the temperature unit Kelvin, and Michael Faraday, Mr. Electrodynamics. Back around 1850, Kelvin and his brothers studied the relationship between pressure and the melting point of water. For example, the idea was that if you stand on an icy sidewalk, the weight of your body could make the ice melt a little bit, creating a liquid layer on the surface of the ice. That layer would reduce friction, make the ice slippery, and suddenly you're not standing anymore. Faraday also thought that a thin layer of liquid on the surface of ice seemed to be the key to making it slippery. And in 1859, he proposed that liquid water always coats the surface of ice, even at temperatures far below freezing. This idea didn't catch on right away, and Kelvin's pressure melting theory was the most widely accepted explanation for a long time. Then in 1939, a pair of researchers proposed it was actually friction doing the melting, not just pressure. Their thinking was that when a material, like an ice skate, is dragged across ice, the heat generated by friction could melt the ice enough to form a thin layer of lubricating water. As it turns out, while pressure melting and frictional melting can play a role, they don't tell the whole story. The arguments start to fall apart when you get to temperatures of about -20 degrees Celsius, where it would take way more pressure than an ice skate pushing down on the ice to melt it. Plus, in an experiment with friction in the 1960s, friction no longer produced enough heat to melt ice at -35 degrees Celsius. But the ice was still slippery. With modern imaging tools, we've finally been able to take a closer look at the atomic structure of ice. And we found that ice isn't such a perfect crystal after all. In a study published in 2024, scientists found that at around -150 degrees Celsius, the surface of ice actually has a mixture of 1H and 1C crystals. And as the temperature increases, molecules near the surface and between the hexagonal and cubic regions become disordered, and the ice loses a lot of its rigid crystalline structure. The disordered layers are still somewhat rooted in place because they're bonded to the bulk of the solid, but they also have some wiggle room. At the surface of the ice in particular, these disordered molecules have dangling bonds that reach outward, like one of those blow-up wavy arm guys from car dealerships. Those wavy arms have a lot of extra mobility, but they also have some elasticity, so they can spring back to their original position. In ice terms, that means the wiggly molecules form a super thin, quasi-liquid layer that's way more viscous than liquid water, almost more like oil. And just like oil, that layer acts as a lubricant, which is why ice feels so slippery. In the end, Faraday wasn't so far off in 1859. Sure, friction and pressure can play a role, but ice is slippery because, well, that's just the way it is. It's a consequence of the imperfections in the ice crystal itself. And knowing that is actually kind of a big deal. A lot of the world's energy is lost to friction. So new ideas about slipperiness could also mean new ideas for lubrication and manufacturing that's more fuel, cost, and energy efficient. Or new ways to make winter sports and winter driving safer. After 100 years, there's a whole world of new possibilities for what we can do with ice.